Okay, let's continue with this derivative from definition in our 2.1 notes. Find the derivative of the following from definition with f of x equals x cubed plus x. Okay, so if I'm looking at this definition, I'm going to have to take the limit, but more importantly, I've got f of x, but I need f of x plus delta x, which means replacing every x with x plus delta x. So that's x plus delta x cubed plus x plus delta x. Now when you cube something, it's like multiplying it together 3 times. You can either use Pascal's triangle, or in this case, you could use the distributive property or FOIL out. It does end up being x cubed plus 3x squared delta x plus 3x delta x squared plus delta x to the third. Here, there's nothing really to distribute, so there's still a plus x and a plus delta x. Now, I have to take this and subtract off my original. So I'm going to take the limit as delta x goes to 0 of this whole thing, x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed plus x plus delta x minus x cubed plus x. And again, can I do that same thing with h instead of delta x? Yes. This is all divided by delta x. Now, as we talked about in the last video, if we're doing this right, everything that doesn't have a delta x should cancel. Now we note x cubed minus x cubed will cancel, and x minus x will cancel, so that will leave us with 3x squared delta x plus 3x delta x squared. If you prefer, we can write it as delta x squared like this so that it's not confusing what the squared is applying to. It's to the whole delta x plus delta x cubed plus x, well, it's not plus x, sorry, plus delta x. Those are the ones that we have left, divided by delta x. And now we can actually successfully divide by 1 delta x. What happens here is that it removes 1 delta x from each term, so that would be 3x squared plus 3x delta x plus delta x squared plus 1. And we can now, we're not dividing by anything, so we can take the limit as delta x goes to 0, which means just plugging in 0 for delta x, which would be 3x squared plus 3x times 0 plus 0 squared plus 1. Now, these two will, 0 times anything is 0, so we should just be left with 3x squared plus 1. Now, taking the derivative from definition can be a somewhat cumbersome process, but this does represent the slope at any x value of the function f of x equals x cubed plus x. Now, besides this version of the definition, there's a slightly different version of the definition that can be useful at times. Again, the way we can do this is the derivative of f at point C can be f of x the limit as x approaches c of f of x minus f of c over x minus c. What this really is just a translation. Instead of centering around 0, we're now centering at the point C specifically. It's not wholly unlike what we did at the very beginning, but there is a representation. And this requires that both one-sided limits exist and that those limits are equal at the point C. Because in order for that to happen, remember that we're taking a limit here in order to find the derivative, and limits only exist if they exist at both sides. Now, if a function is differentiable at a point, it is also continuous at that point. Similarly, if a function is not continuous at the point, it is not differentiable at that point. Now, just because differentiability implies continuity doesn't mean the opposite. You can be continuous and not be differentiable. Absolute value of x or any version of that is a great example. Particularly at the point where it switches direction, the limits are not the same because the slopes on both sides of that point are not the same. And what that means is that it's not differentiable. Generally speaking, when the reason the function could be not differentiable, it could be because of a sharp curve or potentially a vertical tangent line at that point. Something like a function like this, right here, where the tangent line would be like vertical, it wouldn't be differentiable at that point. Now, because we have the ability to find the slope of the tangent line, and we know it goes through that point in question, if we have a point and a slope, we can find the equation of a tangent line, same way we would have done it in algebra, where finding the equation of a line when you've got a point and a slope. So let's look at what an example of that would look like. So find the equation of the tangent line for the following functions at the given point. F of x equals 2x squared minus x at the point 2, 6. So we can use the idea from the formula from the last time to kind of shorthand notation of what this is going to be. F of x minus f of c. So that's f of x minus the y value over x minus the x value of the point in question to find the slope. So let's do that. F of x minus f of c over x minus c, and we're taking the limit as x goes to c. Our c in question here is 2. The y value is 6. Our f of x is 2x squared minus x. So we have 2x squared minus x minus 6 over x minus 2, and we're taking the limit as x approaches 2. Now, the numerator here actually factors. One of the factors in an ideal world should help us cancel out the x minus 2 in the denominator, and it does. This factors into 2x plus 3 and x minus 2 over x minus 2. As we see here, because we have the common factor in the numerator and denominator, this is also equal to the limit that x, as x approaches 2, of just, once these cancel, 2x plus 3, which we can just plug in. 2 times 2 plus 3 is 7. So we know that the slope here is 7. So I'm trying to find the equation of a line with slope 7 and point xy coordinates to 6. I can kind of take my equation for a line, y equals mx plus b. This is m. We have x and y, so 6 equals 7 times 2 plus b, which means 6 equals 14 plus b, which if we subtract 14, that means b is negative 8, and I can return that to the equation. We know that m is 7, so this is the line y equals 7x minus 8 is the tangent line to 2x squared minus x at the point 2, 6. And we'll leave b for you to practice. There's one way we can do this that's also somewhat backwards. Given a function and a slope, find the x value. It has this exact slope in the original function. That means what we're going to do is we're going to find a derivative and match where the derivative, or in this case, the slope of the tangent line, which is m, where it matches, the x value that matches the slope in question. So if I do let's take this one. Let's do b in this case. The limit as delta x approaches 0 to find what we call the derivative. This is 3 times x plus h squared plus x plus h minus 5 minus my original function for delta x. And find out where this whole thing is equal to 0. You can expand this. This ends up being 3x squared plus 6xh plus h squared plus x plus h minus 5 minus 3x squared minus x plus 5 all over delta x. And taking the limit, we can clean this up. 3x squareds cancel, the x's cancel, and the 5's cancel, so we have 6xh plus h squared plus h. We're going to call this over h. I don't know why I'm mixing my forms here, but we'll call them all h. And if we clean this up, this is 6x plus h plus 1. The limit as h approaches 0, which is just 6x plus 1. and I need to see where that's equal to 0, and that will be where x is negative 1/6. And that means at an x value of negative 1/6, the slope is 0. Now if we think about this, this is a quadratic. Where's the slope 0 on a quadratic? Well, it's where there's a horizontal tangent line, a slope of 0, and that should be at the vertex. Generally speaking, for a vertex of a quadratic, that exists at negative b over 2a, which would be negative 1 over 2 times 3, which is negative 1/6. So it's kind of an interesting application, and that's really all for 2.1.